So it looks like we're into, if I lose count, this is the third sort of video, emergency style video, just to kind of capture this so students can get either a slightly different presentation of the material or just to sort of reiterate what's taking place in class. This previous video had left off with introducing the 4 quantum numbers, right? So talk about the number of orbitals that you might have. So now that we have we're going to retouch on the quantum mechanical version, the 1 electron only atom versus the rest of the periodic table, which is essentially more than 1. So we'll touch on the electron correlation problem, effective nuclear charge, and a little bit on SCF orbitals, if you will. That is all in your first year textbook. You can read up on the appropriate sections that talk to that. Then we will move on to electron configuration, but maybe we'll tidy up the quantum model first. So what we have, let me get this straight. So we talked about single electron system. So if you have a 1 electron atom. Now, oftentimes, this is when a lot of books, and even I'm looking at a chart of orbitals, hydrogen orbitals. So in other words, we'll reiterate, the hydrogen atom with 1 electron, when you solve the Schrodinger equation, you get exact solutions, okay, because there's only 1 electron. And it's the nature of these exact solutions that led to the idea of the 3 quantum numbers. And it's the 3 quantum numbers that specify, for example, possible orbitals that an electron with the appropriate energy inside a 1 electron atom system could become. The electron becomes the orbital. Now, we have to be a little careful. A lot of times we almost imagine that, for instance, a 2p orbital actually exists and is waiting for an electron to occupy it. It's actually incomplete. One of the latest interpretations, or even the Copenhagen interpretation, or the Born interpretation, if you will, is that the electron itself becomes the orbital we talk about. The electron, especially when you're not interacting with the system or measuring an observable outcome for its whereabouts, it gets spread out in whatever this delocalized, spread out electron configuration or electron density is. So the possible orbitals that an electron could be or become. Off to the side on that, the magnetic spin, that is actually for an electron. It's a property of the electron itself. So it's a quantum number that belongs to the electron. It can either have the sort of the analogy, or the way they talk about it, is spin down. 1/2 spin down is what they'll say. But there is no physical meaning that they actually have for the concept of spin. The only thing that they know is that inside an atom, if the electron is existing as a orbital, if you will, the electron itself has some vector quantity, right, that is distinguishable in a magnetic field. So in other words, this little side analogy says, if you had 1 electron inside here, so let's just put 1 electron is a 1s orbital. So this is the thinking bubbles. Is it technically spin up or is it spin down? Right? That's the analogy. Well, the only way you can do it is, let's say that you had two hydrogen A and over here hydrogen B. And you have 1 electron, that's both of them. And let's just say that it happens to be, for both of them, ground state, the 1s orbital that the electron has become. Well, if this was your side energy ranking, if there's no magnetic field present at all, there's no way to distinguish the one electron in either of these hydrogen atoms. There's no difference between spin up or spin down. But put them, here's your energy, but put them inside a very strong magnetic field. So take the two of them, whoop, insert them, and these will all of a sudden separate. Whichever one is which, one of these, let's say one of them was, in something that only, God only knew what it could be. But let's just say that one of them, if they turned out to be lined up with the field, this vector quantity related to what they're calling spin versus the other one. So the one that's lined up with this field will be lower energy, and then the other one will be higher energy. So now there is an observable energy difference between these two states, right? So that's the idea, and that is a property that belongs to the electron itself. So when we go back here, a lot of your questions, and we'll do some of them, they'll say, what are the possible orbitals that an electron, some books will say what the electron could be in, or that what are the possible orbitals, period, depending on the wording. So those are the quantum numbers, the three of them, that relate to the characteristics of the orbital that the electron can become. So that takes care of that. For more than one electron atoms, so that's pretty much everything else in the periodic table that we may deal with for electron configuration and questions of trends in the periodic table in a little bit. And the other thing was the one electron, we want to reiterate it again. We know that when one electron only systems, you have the 1s, the 2s, the 3s, the 2p, the 3s, and the 3d. It's the principal quantum number where all of these orbitals are degenerate that have the 3 in it and the 2 in it. But that's only for this. When you go to more than one electron systems, and I now actually have a nice big chart that I've posted. This is what we talked about last time. For more than one electron systems, they found a way using the SCF, self-consistent field method. They found a way to sort of average, if you will, all of the electrons. Each electron, it's almost as if they're going to say, okay, let's focus on this one electron in the atom, and all the other electrons, we're just going to treat it as one averaged out entity that doesn't move or have any correlation issues. So they make some big approximations to kind of preserve the use of the quantum numbers. And it was successful in that simpler model to keep the quantum numbers, so you can still talk about 1s, 2s, 3s, 2p's and all that. But the energy now, the relative energy spacing of these orbitals follows this progression, which I might as well talk about it right now. Notice how you start with the 1s filling it in, you go to the 2s, you go to the 2p, then you go to the 3s. Folks, all you need is a periodic table. And I'll often say this in class. So this is the S block. See how they're only two wide? Because an S orbital, it doesn't matter if it's a 1s, a 2s, a 3s. And I might also make the giant note right now. This is your S block. And it's written right down here on the bottom. It says S block right here. Now these numbers on the side, be very careful. It happens to match the S principal quantum number, S number, if you will. But these numbers refer to simply the horizontal rows, the first row, the second row, the third. So if we cover these up and we're talking about the S block, you could say the hydrogen box, if you will, like pretend hydrogen wasn't there, is the 1s1. So if I was filling in hydrogen, I would say it's the first box on the periodic table. So one electron goes in there. Then you go to helium. That's like putting a second electron in the 1s orbital. What's next? Well, the periodic table says what's next is these two square boxes under the S block. So this is going to be the 1s, this is the 2s, the 3s, the 4s. But the progression of the periodic table tells you this automatically. So all that diagonal memory device of electron configuration, when you have one of these in front of you, it's kind of pointless. So notice, after your 2s, you move on to the 2p block. And of course it's 6 boxes wide because the 2p has 3 orbitals, each can hold 2 electrons. And after neon, you come right back to, cover this up, this is the 1s, the 2s, this is the 3s. And after the 3s, this chart is already laid out to follow what the periodic table does. It jumps from magnesium over to aluminum. So what you could do if you want, and this is where this block is the 2p block. This is the 3p, 4p, 5p, 6p. Now, the P block and the S block actually follow these horizontal row numbers. Where it starts to break down is when you get to this is the 4s, but the thing that fills in next after 4s goes to 3d. Well, that's exactly what the periodic table says. After calcium, you go to this D block right here, 10 boxes wide. But see how this is the 3d, not this 4, which is just which row in the periodic table is. So you need to almost make a note. This first bunch of D's is the 3D. So I think you get the gist. You can look at this periodic table and you can recreate this relative energy ranking of what orbitals get filled. This is an energy level diagram for any atom, and you can just fill it in and make copies of it if you want, okay? So that's what that is. So I just wanted to talk briefly and put something to sleep here. There is an important section in your book where they're going to talk about polyelectron or polyelectronic atoms. And somewhere in that text, they're going to talk about what's called the correlation problem. So again, the note is, when you go back to 1 electron systems, the Schrodinger equation can be mathematically solved exactly for 1 atom-only systems. Perfectly exactly, shows the birth of these 3 quantum numbers. We already covered the principal one, the shape, and the number of orbitals of this shape that can exist in groups. We know that. But when you have a polyelectron system, the correlation problem is this. When you have a positive center that's going to act as the cage or the trap of your electrons, so let's say that you had, and I will draw, let's say you had a couple of electrons and further out you had another one. Well, here's the problem. Because these darn electrons, when in a quantum state, it's almost like if you're not looking, all 3 of these is going to exist in some kind of shape and type of electron density. And if you're not looking, they don't exist all the time as existing chunks of matter that are always there whirling about, right? So this spread out electron density, if you will, but it still has the problem that any one of these electrons, if you go looking for it, where can I find you? In the way that these different electron distributions can be gone about. So what I'm going to show you is, well, before I get there, there's a couple things they can do. One of the things is they talk about what's called effective nuclear charge. So the concept of effective nuclear charge, which is in your textbook, basically says the simplest way to go about addressing, as soon as you have more than 1 electron, how do they interact? And it's always changing with time. So they're saying, why don't we just sort of say, each electron that we happen to be looking at, so if we happen to be looking at, let's just say it's an electron at a higher energy level that we want to call it like a 3p electron. Well, what are these 2 electrons doing? And a lot of times if it's ground state, they could be 1s or a 2s electron or something like that. But the point is, how much of this positive nucleus does this outermost electron that you're trying to model, and like we said, just for example, what if it was like a 3p type of situation? How much of this positive charge does it feel, if you will, or sense, when these damn things are changing with time, wherever they could be observed, or what their electron density looks like? So there is a way of saying, let's just pretend that these electrons are not correlated to this one's existence at all. Let's just pretend that they have some sort of averaged out electron density, so that this one sees an averaging effect, if you will, the effective positive charge. It's a very big assumption, approximation, but it does lead to certain types of results. That's one way to do it. Now there's another way right? So what they're going to do with this effective nuclear charge type thing, when you apply quantum mechanics, you get a different slight approximation, and you get slightly modified, for instance, s orbitals or p orbitals. There's slight modifications to it. Now, they're not going to show us exactly what that means or pictures of it in the book, but they're letting us know this is one way to do it. But they're saying that this oversimplifies. Maybe this approximation is too simplistic. Oversimplifies. So that's right out of your book, the very concept that this is one approximation to deal with it. The only reason why I'm bringing it up is a lot of people still talk about effective nuclear charge. And I think it's even in one of our inorganic courses or something like that, where this is still often talked about, right? Even though we don't specifically start drawing pictures of the electron density. But one other approach that we do use, right, is we would say, and this is called, make sure I get this right, the self-consistent field method, SCF. And it turns out that this particular way of trying to address more than one electron and how they are actually correlated to some extent, we don't want to oversimplify it with effective nuclear charge. But this is more or less the accepted one that allows for a couple of things. This method allows we keep the NLML quantum numbers, right? Right? We can get the relative, and we already talked about it, but this is the real thing behind it, the relative energy. The relative energy states with NLML relative. You don't get the exact energy differences from the calculation. You just get the relative ranking of the energy states and how you can fill it in. That's what the benefit of it is. You still get to talk about, 3P and 3D and things like that. That's all kept. But it's still an approximation. You don't get the actual energy differences between them. Like in a one electron only, we can calculate dead on the energies of the states and the differences. So it's almost like each and every electron gets its own calculation done, right? It's a different way of averaging out what the rest of the electrons are doing. So it's related to the effective nuclear charge method in a way, but it is better. So if you want to learn more about that, you can look it up. This is what allows us to generate these energy level diagrams that we know very well, and how the periodic table is still set up this way and how we keep these. But make no mistake about it, folks. Many electron systems, these quantum numbers, this is a model and an approximation of it. And even the shapes of these individual orbitals is still based on the one electron only systems as well. So all these orbitals, when we're trying to draw a quick picture of them in organic chemistry or beyond, it's still uses the hydrogen orbitals, including their shapes. The reality is many electron systems, orbitals are different. In a lot of cases, they're very similar, but there is going to be some differences. So you can't take them perfectly literally. But for most chemistry purposes, keeping this analogy is way more than good enough, okay? So I think we talked about that. That's not bad. So what I'm going to do is I think we're going to move on. So I'm going to pause that, and we'll start another segment very shortly.